Now here I'll discuss plane polarized light. What is plane polarized light? Let's try to understand first what is plane polarized light. Alright. See, when I say light, I mean light beam. Light means light beam. Now, light beam consists of infinitely many rays. Light beam consists of infinitely many rays which share a common property that they have the same direction of, they propagate in same direction. They propagate in same direction. So light beam consists of infinitely many rays and they share a common property, they propagate in same direction, right? Each ray can be seen as an EM wave. I can see each ray as an EM wave, and EM wave is characterized by two fields, E and H. But these fields are not independent of each other. Once you know E, you can get H. Once you know what is the electric field, you can very well find what is magnetic field. So E and H are correlated to each other. E and H are dependent on each other. E and H depends on each other, right? So it's enough to describe an EM wave by one of the vector. Because once you define one, once you write one of the vector, other vector is determined using Maxwell equation that we have seen, right? So E and H are dependent on each other. E and H is enough to write only one vector, other vector gets specified. Now, when you have a light propagating in this direction, suppose light is propagating in this direction, means you have different beams of light, different rays of light. This is a light beam. What I am saying is, this is light beam, and this beam will consist of infinitely many rays, and these rays are all propagating in one direction, forming a light beam. Now, the field vector, when I say field vector, I mean either E or H, right? So when I say field vector, let us characterize the field by the EM wave by one of the field. Let's suppose I am characterizing the EM wave, I am describing the EM wave by one of the field vectors, say E. I won't call it E, I'll call just field vector, right? So the field vector, that is E vector, for all these rays must be perpendicular to this direction of propagation. From electromagnetic theory, we know that the field vector must be perpendicular to a direction of propagation. So if this is a direction of propagation, your field vector can be in this direction, or it can be in this direction, or it can be in this direction, or it can be in this direction. All are perpendicular to direction of propagation. Perpendicular to direction of propagation, you can infinitely many directions. But all these directions will be confined to a plane which is perpendicular to the direction of propagation. All these field vector will be confined to this particular plane, a plane which is perpendicular to the direction of propagation. If I draw a plane perpendicular to direction of propagation, all these field vector will be confined to such a plane. The field vector will be confined to such a plane. So you have the field vector associated with each ray will be lying in this plane perpendicular to this direction of propagation. The plane is perpendicular to the direction of propagation. So the field vectors of the rays which forms a beam will be perpendicular to the direction of propagation. So they will be confined to this plane which is perpendicular to the direction of propagation, right? Now let's try to define when do you call the light to be plane polarized, right? Suppose before that I'd like to define what is unpolarized light. Let me first define what is unpolarized light. Let me first define what is unpolarized light. See, in case of unpolarized light, see, if this is the direction of propagation, right, and let's consider a plane which is perpendicular direction of propagation. Now consider, see, I told you it can lie, the field vector can lie in any direction which is perpendicular to the direction of propagation. Means it can lie in this plane, any direction which is confined to this plane will be perpendicular to the direction of propagation, which is characterized by, say, n vectors, right? Now in this plane also you have infinitely many fields, you have infinitely many directions which you can draw in this plane, right? And all of them will be perpendicular to n. But you have two independent directions. The number of, if I ask you what is the number of direction which you can have perpendicular to this n, obviously then you can find this plane. Here are infinitely many directions, right? But if I ask you what is the independent direction, what is number of independent directions, suppose this is z axis, then you have two independent directions, one is along x, other along y, this is y. So x and y are two directions, right? This is described by I vector and this direction is j vector. The rest of the direction can be written as linear combination of I and j. Any other direction which is described by a vector A can be written as linear combination of I into some constant into j. I can define rest of the unit vector, rest of the direction can be described by a unit vector which can be written as linear combination of I and j. I can describe them by linear combination of I and j. Any unit vector drawn in this plane can be written as linear combination of I and j. Any unit vector which characterizes a direction can be written as linear combination of I and j. Now, so it means, see, you have infinitely many rays in this beam, and the only condition which EM theory, electromagnetic theory, put on the direction of field is it should be perpendicular to n. So it can lie in any direction. Any direction. If suppose, means the meaning is you have many directions in this plane and all the directions are equally probable. All the directions are equally probable. A light ray has equal probability of aligning its field in any of the directions. None of the directions is preferable. All the directions are equally probable. So if I ask you, if suppose I define this, suppose I have, say, a number of rays, say if I draw a vector, say here, if I draw a direction, say making an angle, small angle with t, x-axis, suppose this direction. So, and suppose I draw a direction here making the same small angle with y-axis. Then if I ask you the number of rays having field vector in this direction, and what about number of rays having field vector in this direction, this would be equal, because this direction is equally probable. When all the directions are equally probable, I can say the rays are equally divided in all the directions, all the possible directions. You have equal number of rays having field vector in this direction, you have equal number of rays having field vector in this direction. That's something which I am telling based on the probability. Since none of the direction is preferable, provided they all are confined to this plane, every direction is equally probable. So if I choose two directions, it need not be at the same angle theta. If I choose any directions, the number of rays having field vector in that direction will be equal to number of rays having field vector in any other direction. Number of rays having field vector in this direction, number of rays having field vector in this direction should be equal, because every direction is equally probable. Because every direction is equally probable, right? This ray, this direction is equally probable than this direction. So if I have, say, n number of rays having field vector in this direction, we'll have n number of rays having field vector in any direction. Suppose I choose this direction, it may not be theta, it may be different from theta also. So if this is n number of rays having field vibration in this direction, then n number of rays will be having field vibration in this direction as well. So number of field vectors in every direction should be equal, because every direction is equally probable. If we have such a thing, it's called it unpolarized. In case of unpolarized, you have equal number of field vectors in every direction. Every direction equally probable. If I ask you what is number of field vector in this direction, it will be same as number of field vector in any directions, right? So this is unpolarized. If suppose, to be very precise, if suppose you have a field vector in this direction, then this field vector can be written as E equals to, suppose this is E equals to E naught sine kz minus omega t. Say, draw a red pen. This is E naught sine kz minus omega t. This field vector can be written as E naught cos theta I plus E naught sine theta right. So in that case, what is the intensity of x vibration? This is nothing but EXI plus EYJ. So what is intensity of the x vibration? That's going to be, intensity of the x vibration is E naught square cos square theta, where intensity of the y vibration is E naught square sine square theta, right? If suppose theta is 30 degree, then this is going to be 3 by 4 E naught square, and this is 1 by 4 E naught square, right? So 3 by 4 E naught square, and this is 1 by 4 E naught square. So you have higher intensity towards x, lower intensity towards y. Now let's suppose the E vector makes an angle theta with the y-axis, makes an angle pi by 6 with the y-axis. In that case, I can write E as E naught cos theta or E naught sine theta, that is sine pi by 6 I sine kz minus omega t, right, plus E naught cos pi by 6 j omega t, right? So in that case, your intensity towards, in that case, your intensity towards x is E naught square, that's going to be E naught square by 4, and intensity in y direction is the 3 by 4 E naught square. Y direction is 3 by 4 E naught square IY, right? So you have, when the field vector makes an angle 30 degree with x-axis, you have 3/4 of the intensity in x direction and 1/4 of the intensity in y direction. When field vector makes an angle of theta degree pi by 6 with y-axis, you have 1/4 intensity towards x direction and 3 by 4 intensity in y direction. Now, for every field vector making an angle 30 degree with x-axis, there exists a field vector making 30 degree with y-axis. I can say this. For every field vector, since every direction is equally probable, for every field vector making an angle theta with the x-axis, you have a field vector making a smaller angle with y-axis as well. For every field vector making a smaller angle with the x-axis, you have a field vector making the same amount of angle with the y-axis as well. So in this case your ix is higher, in this case your iy is higher. So if you add these two, sum of ix and sum of iy, I break all the fields like this, exi and eyj. If I break all the fields like this and see the contribution in ix and iy, what do I say? See, the number of rays are infinite. So from the probability, I can very well say, if you have a field vector making greater contribution with to x, then you have a field vector making greater contribution to y. And in that case, I can safely say your total intensity ix, sigma ix, and say sigma iy should always be equal. Intensity will be equally divided in x and y. Intensity of all the x vibration and intensity of all the y vibration must be equal, and that should be equal to I naught by 2. That's the case of unpolarized light. If there is any mismatch, if you have sigma ix greater than sigma iy, it means the direction closer to x-axis is more probable compared to a direction which makes a smaller angle with y. That's why the contribution to ix is higher than contribution to iy, and that's why the mismatch. Contribution to ix is higher than contribution to y. That's the case of partially polarized. If sigma ix is less than sigma iy, then the electric field makes smaller angle with y compared to x. So direction which makes smaller angle with y is more probable for the field vibration compared to the direction which makes smaller angle with x-axis. That's why your ix is less than iy, sigma ix is less than sigma iy. That's also the case of partially polarized light. That is also the case of partially polarized light. Get your point? If suppose the direction of all the field vector, direction of field vector associated with all the waves, direction of field vector associated with all the rays are lying in one direction. Direction of field vector associated with all the rays are lying in one direction. In that case, the light is called plane polarized. This direction can be this, it can be this, it can be this, but whatever it is, all the rays are field vector in that direction. That's called plane polarized. And plane polarized is also called linearly polarized. Plane polarized light is also called linearly polarized. So I hope you understand the difference between unpolarized, plane polarized and partially polarized light, right?